Up until now, we spent a lot of time developing various parts of the calculation for different coefficients in the transfer function, right? We found a way of calculating the a1 and b1 in the transfer function, in a generalized transfer function. So a generalized transfer function for a system, let's say that has an input x and output y with multiple elements. Let's say you have C1, you have inductor L2, some elements here Ci, you can have other elements Cj, and all the way to n elements. This can be viewed as a system with no dynamics or no energy storing elements inside, with all the energy storing elements attached to it from the outside as an appendage, right? And we know that the transfer function of something like this in general has this form. We've written this many, many times, so I'm going to write this very quickly. All the way to am, and then there's a 1 plus b1s plus b2s squared all the way to bn, s to the n, and there's a m, s to the m here. So far, we know exactly how to calculate a couple of these coefficients. Which ones do we know how to calculate? Well, a0 is a low-frequency transfer function, right? Which basically is calculated, which say a0 is h0, superscript 0, meaning that it's the transfer function when all the elements are zero valued, right? When you set all the elements, so all the capacitors are open, all the inductors are shorted, you see it's a DC calculation, right? Everything will be a DC calculation, but this was the first one, right? So then the other thing that we did, we calculated A1 and B1. B1 was the sum of the zero value time constants, right, from 1 to n. Well, let's make this n prime, n prime. N, the number of elements. This is n, the number of elements. So, and what were the zero value time constants? Zero value time constants where you look at the resistance seen by one of these elements where all the other elements are zero valued and all the sources are null, independent sources are null. You look at that resistor. If it's a capacitor, it's that capacitor times that resistance. We call those resistances, so these were either, so where tau I0 was either Ri0, the resistance seen when all the other elements are zero valued, times Ci, or if you were dealing with an inductor, alternatively, tau I0 was Li over Ri0, right? And then we had element A1, which we calculated to be exactly, these are all exact, and everything with the TTC is exact. 1 to n is basically tau I0, the same zero value time constant, but scaled by what we call the first order transfer constants, hi. So what is hi? Hi was the transfer constant, meaning it was the transfer function when all the capacitors, where capacitor, the element I, in general, or capacitor inductor, is infinite valued, and we know the rule is that anything that's in the superscript is the index of the element that's infinite valued. I've said this several times. And all the other Cj's are 0 for j not equal to I. So, or Lj's, whatever. So what happens is that basically to determine hi, what you did, you said, okay, let's say this element, Ci, I make this infinite value. So in this case, it's a capacitor, it becomes short circuit, but everything else is zero valued. And you look at this it still is a DC transfer function, transfer constant, right? So these are the things we already knew. So now what we're going to do, we are going to determine all these other terms and see what they are. Now, and I will give you the answer up front. Okay? I don't want to keep you in suspense. So I'll tell you what the answer is, and then we'll see why. And the more detailed derivation is also in that paper that you have. So the answer is this. So let's go to B2, for example. So what is B2? So B2, I'm going to write the answer and I will explain what it means, is a double sum over I and j, where I smaller than j, and I and j they go between 1 and n, but they don't repeat. So if you have covered 1, 2, you don't cover 2, 1, of tau I0 which are the zero value time constants, tau ji. Now, if we've thought about our notation and if we've been clear about the meaning of things in our notation, well, this is clear. This is the same thing. This is tau I0. Right? What is tau ji? What does it mean? What do you think it means when you have a superscript I? It's the...
So you infinite value element I.
Yes. Right. The time constant associated with elements j when element I is infinite valued. And everything else that's not listed is still zero valued. So it's very similar to the zero value time constant, except for the fact that now element I is infinite valued. In the case of a capacitor, it's short-circuited. So you do the similar calculation, except for the fact now instead of keeping Ci open, you do Ci short. And you see what the time constant is. Right? I haven't proven this yet. We haven't proven this, but yes. No. No, element J is element in question. We don't really care. We are caring about the resistance seen by element J. We are looking at RJI. So it's neither infinite valued or zero. You can think about it as being removed. You're only looking at the resistance seen by it. That's a good question, right? Because if you zero value it, essentially, if you infinite value it, you've shorted it. You can think about it as being not there, being zero value. Right? So the subscripts are always associated with the element in question. The superscripts are the elements, is the index of elements that are being infinite valued. And that's all you really need to know to understand this notation. So, and then B and A2, what do you think A2 is? I mean, if you look at this and extrapolate. Well, first of all, A2 still has to have units of H. So there has to be a single H in it. Some sort of it has to have one transfer constant. And if you extrapolate from this, I mean, we don't need to. I mean, this is the answer. But it should also feel natural. That it's the same sum of tau ij and the same exact two time constants, or pairs of time constants, more accurately. It's not just one pair, times hij. So it's weighted. It's the same sum. It's a similar sum, but now these are weighted by hij's. What does hij mean? Both I and j are infinite valued. In this case, both capacitor Ci and capacitor Cj are shorted. And everything else that's not listed is open. Or well, zero valued. If the capacitor is open, it's an inductor is short circuit, right? So, and in general, Bn, well, whatever, you can pick one, B lowercase n, is going to be an n sum. So let's just basically, so you could go from I, j, k, however many sums till you get to n of these, where you have I smaller than j, smaller than k, smaller than dot, 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 smaller than n. And this looks messy, but it's actually not as bad when you actually start calculating these things. And then the sum of the time constant, the product of this time constant, tau I0, tau ji, tau kij, etc., etc. Remember, you will always have only one subscript for these taus, but you can have multiple superscripts, because the superscripts are the indices of elements that are infinite valued. So that's generally the element n, the Bn, and An, again, similarly to the other ones, is the same sum, or sums, sum of sums, of I smaller than j, smaller than k, dot, 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 smaller than n, the same time constants, or time constant products, dot, 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 h, I, j, k to the nth. So this is the answer. This is the generalized time and transfer constants. Now, we will do a lot of examples for you guys to see how this is applied. And you will see that when you apply it, you don't need to write as many terms. And you can see some of the properties of when it's applied. But before we do that, let me at least show you part of the derivation of where it comes from. Right? So in this setting, you remember when we said we have something like this, we could write the transfer function, and we did this before. We can write it in the following form. You can write this transfer function as h of s is a0 plus, and then we did this when we did the derivation, for example, of the zero value time constant calculations, right? I equals 1 to n. We wrote it as alpha 1 I. I'm sorry, alpha 1 I, yes. CIS. So we argued that the first order terms have to, when we did this, we argued that the first order terms come from product of capacitors and inductors, right? Because the only way you get an S, a complex frequency, is either through a CS or an LS in your transfer function. So the first order terms have to be first linear combinations. So this term, if you factor the S out, this is your A1. And similarly for B1, has to be a linear combination of the capacitors. So this was your A1 and B1, and we did this derivation before. And then we said there are actually higher order terms. We actually wrote the higher order term, the second order term, when we were doing the derivation. And the second order term was this sum of beta, it's a numerator, it's alpha 2 ij ci cj s squared. And similarly in the denominator, the same sum. Sometimes I may drop the smaller than n greater than 1, smaller than or equal n greater than or equal 1 when I write this. So that's shorthand notation for that. Right? And we did calculate these things, right? So let's think about this is purely a capacitive only one. You can do an inductive and capacitive mix. It would get the same result. Just have to write two sets of sums for each one of them. It makes it even messier looking. But it doesn't matter. So the key is this. So one of the things that we observed back then was, if you remember, was that you cannot have CI here. You cannot have the product of, you cannot have CI squared. And you remember why, right? Because if you had that, you could, if you set all C's except for CI to 0, right, you should get a first order system. If you have all elements 0 valued except for element I, well, we can do it with capacitors only, C2, CI, CI, CJ, etc. Now, if you had only capacitor I non-zero and all of the other capacitors 0, you should get a first order system, right? If you have a CI squared here, you'll get a second order system, and here too, right? So they cannot be repeats by that argument. So that's why this sum works this way. It's I smaller than j, not smaller than or equal j. Okay, so fine. So we did calculate these things, right? What was alpha? What was beta 1 I? I mean, what is beta 1 I? If you have just purely capacitor stuff. It's that resistor, right? Seen by capacitor. It's Ri0. Right? It's a capacitor resistance seen by element I when all the other elements are 0 valued. Ri0. We did this part of the derivation for. And alpha 1I was what? Was Ri10 Hi. We had done these calculations. This part we have done before. So we can use those results. Now the question is, what are these, the next level, right? So how do we calculate those? So let's start with the situation. So to calculate those, let's do this, apply this condition. Let's say Ci is, yeah, okay, let's apply, just to be sure. Okay, yeah, Ci going to infinity and Cj being finite, okay, and Cj So we apply this particular condition to isolate one of the terms. And the other ones are finite, or they're 0. Right? So what happens if ci goes to infinity? If I set ci to infinity, let's just think about the terms that we see on the whiteboard. Let's not worry about the higher order terms. What happens? And let's say all the other, let's say ck equals 0 for k not equal to I not equal to j. So this, what this condition means is that this guy is short-circuited here. This is this is there, and these guys are open. Right? That's what it means. So what would happen to these terms? If ci goes to infinity, would this term and would these two terms matter? No, because they're finite compared to something that's multiplied by infinity, right? So these terms will disappear. So what will you get? So what you will get is that you will have a ci, 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 and ci here, right? So you can factor all those ci's out. So what do you get when you factor those? So you can actually write, I can factor it out. I can factor cis out. So you get a cis and cis. And what is left from that one would be what? From that first term, there's only one thing left, right? What would be the thing that's left from the first one? It would be alpha, so this is multiplied by alpha 1I. Because all the other ones are negligible compared to that. Or either explicitly 0 or negligible. And here you get beta 1I. So I'm just basically showing it the part of the derivation to you. And then what is left from these guys? The only thing that's left is the things that are multiplied by ci, right? So what you get is alpha 2 ij cjs, and you get beta 2 ij cjs, right? So that would be the dominant term for this. And everything else would be 0. And this makes sense because you have to get a first order system, right? You only have one non-zero, non-infinity capacitor in the system. There's one, Cj. So this is the transfer. So these two obviously cancel in the limit when Cj is going to infinity. It doesn't matter. This is in the limit when the Cj goes to infinity. And so this is what you have. So what we are trying to calculate is what? We know, but do we know what, for example, this term is? If I factor beta 1 here too, so let's say if I factor from the denominator the beta 1i and from the numerator alpha 1i, what is left is 1 plus alpha 2ij over alpha 1i cjs. And in the denominator you have beta 2ij divided by beta 1i cjs. Right? Now, this term, do we know what this is? What's the value of that? Well, this is the first, now you have a first order system. You have a different first order system, but you still have a first order system, right? For this first order system, what is the time constant? What is the denominator? That should be, this whole thing should be the time constant, right? This whole thing. That is the tau of this new system. What is the tau of this new system? It's the resistance seen by this guy when these other elements are all zero valued except for element. So this is the resistance seen by element j when element I is infinite valued. Do you agree? Times Cj. So this part of it then, so this part, this beta 2ij divided by beta 1i is rj superscript I. Right? But we have already calculated beta 1i, right? So if I plug that in, I get the beta 2ij. So beta 2ij is going to be ri0 rji. And then look at what is multiplied by. Oh, here, what's multiplied by? It's ci and cj, right? So this entire thing is what? Is Ri0, Rji, Ci, Cj. I could write it this way, or I could regroup them in a cleaner fashion, right? You could regroup them and say, look, hey, these guys are just that first time constant. And these guys are that second time constant. So what you can do, you can then write this as tau I0, tau Ji, which basically proves this, right? And then you can do exactly similar thing with the alpha to this ratio in terms of those, and then once you write it in that terms, you will see again, this is the same thing, you calculate it, you will get the same result. And you can keep doing this to higher order terms, and that's how you prove these terms. I've messed up the order of my whiteboards. I should have used this one next, but anyway. Now that's kind of being obscured. But did everyone get this? And okay, so I'm gonna, if you got this part, I'm gonna just switch to the, oh, here. Okay. And then so I'm gonna switch back to this guy and what we have. Okay, so that is the big result. That is everything. This is called generalized time and transfer constants. So you can calculate all the coefficients. You don't need to write a single high frequency KCL or KVL, and you can calculate it to the degree you want. Now, the thing to remember is that you can calculate exact transfer functions using this, and I'll show you a couple of examples of that. But the good news is that unlike writing KVL and KCL at high frequency or doing nodal analysis, you can stop, right, halfway through and get partially useful results. You can say, okay, you know what, I really care about B1, and maybe A1, and maybe B2, so I'm going to stop there. Or I'm going to get a sense of what my Bn looks like from this time constant. It would be this constant, it would be dominated by this or that, so you don't have to write the entire thing, simplify a bunch of RCs and LCs and things of that, so RLCs, to get to the final result. Again, we built up, we spent time invested in this to use it as a design tool. And I'll show you some examples of that. Any questions about the general derivation? I did not prove it in general for the n, technically, but it's the same derivation. So basically, what you do for the next one, you take Ci and Cj to infinity, and you look at the finite Ck, and those terms will pull out. Yes?
So obviously, like your An or your Bn have to stay the same if you just reindex all the elements. But I guess, to me at least, it's not immediately obvious why reindexing all the elements would never change those sums.
Oh, that's a great question. So you're saying that there are many different ways to calculate reindexing this string, right? So, well, so you say, is it obvious that the reindexing, I was actually going to show examples of that. But well, good, no, it's good question, so let's answer it now. You say, why would reindexing them, reordering the indices would produce the same result? Well, if this result is correct, so I could make an argument, kind of like a high-level argument, say,
I know physically it has to.
It has to be the same, right? But is it going to be the same thing, right? So it's basically from the argument that there's a single transfer function, right, for this. And if the single transfer function is not dependent on, I wanted to actually use it the other way. I say, well, if it should not change by the choice of the indices. So the reordering of the indices should not matter. And you will see it in practical examples that I'll show. So that actually you don't need to calculate all of them because it's not that you need every combination, you just need a few. And sometimes certain reindexing makes it easier to calculate some of these things. Because in general, the higher order of these things are actually easier to calculate. You can imagine why. But there are more things that are short-circuited, more capacitors that are short-circuited. So those time constants becomes kind of almost trivial. You look at, well, this is short, this is short, this is short. There's like one resistor here sitting, right? That's it. But let me show you examples of that. But I mean, the argument is that if the mathematical proof is correct, then the indexing should, because we didn't make any assumption. But it may not be visible, and hopefully once we do examples, it should be. And if it didn't, let's talk about it more. Any other questions on this? Okay, let's take a little break, and then we'll come back and do a bunch of examples of this and see how it applies.